Hello, good afternoon. This video is for Stat 110 and includes a discussion of the study guide for exam number 3. Exam number 3 is going to be on Wednesday, April 24th. It is going to cover sections 5.1 through 5.3, sections 6.1 and 6.2, and also section 7.1. Quizzes number 10 and 11 are relevant for exam number 3. Study guide and solution is provided at Stats class. Okay, let's go ahead and talk about the solution here. So up first we have a set of questions mostly out of chapter 5 here. Suppose scores on an exam range from 0 to 100. A score of 50 must be equal to the median or the 50th percentile. That is false. We could have one person that scored a 0, a whole bunch of people that scored maybe in the 80s, and then one other person that scored in the 100. The 50th percentile would be in the 80s then, right? So it doesn't have to be halfway between the maximum and the minimum. B, the average is measured on the same scale as the data. Yes. If data is measured in dollars, then the average will be expressed in dollars as well. Standard deviation is also measured on the same scale of the data, so that is true. D, the range is the most widely accepted method of measuring spread. That is false. That would be the standard deviation is the most widely method used to measure spread. E, that is true. The standard deviation uses all of the data points in the calculation. Again, the standard deviation is just the average distance back to the middle, and it does use all of the distances back to the middle in its calculation. Z-scores are used to identify outliers. That's true. The cutoff rule is indeed below a -2 or above a +2. Those would be considered outliers. And then a t-test does allow us to expand the scope of inference. Anytime I'm doing a p-value, we are trying to expand our scope of inference beyond the data that we've collected. Okay, let's talk about 2 and 3. This is about my drive to work. It takes about 30 minutes typically. And this is asking what would I have to do to change the center or location of that data? Well, if I drove faster every single day, then the center or location would shift down a little bit. It wouldn't take me 30 minutes, but it might take me 25 minutes, for example. Or I could slow down every day. So instead of 30, it would maybe take 32 minutes. If I want to start changing the variability, then I need to drive slower on some days and faster on other days. So I get more variation in those measurements. Okay, let's talk about the next one here. So this is looking at these 3 different snowfall amounts where I have made a statement that the further north I am, so further up in this picture, we can expect more snow. So I have original data, new data 1, new data 2 here. You can see that new data 2 has all of the weather locations in northern Minnesota, so I can expect that average to be larger. B, we expect the original data would have the smallest standard deviation because it has the fewest number of locations. Our measures, like average and standard deviation, are not influenced by the number of locations or the number of data points, so that's going to be false. None of our measures that we typically use are influenced by the number of observations. That wouldn't be a very good measure. We'd expect the average of new data 1 to be about the same as the original data. Well, all I've done here is just added one more location to both the northern and southern Minnesota, so that average there is probably not going to change much. We'd expect the standard deviation to be the same about. That's true as well. Just adding a couple more, but I added one on the high side and one on the low side, so those are going to kind of even each other out. We would expect the standard deviation for new data 2 to be, smaller. That is going to be true because these are geographically closer to one another. And they're all going to have, they should have higher snowfall amounts, but they should all be more similar to one another. So new data 2 is probably going to have a smaller standard deviation here. This is just a question about if I were to add 5 extra points to some of the data values, that is definitely going to increase the average, but it's not going to change the median. I would have to have half the data I would have to add these additional 5 points to half of the data before I would start influencing the median. Statisticians say that the median is more robust against outliers. That is definitely the case. So the outliers and these changing data values are going to have more of an impact on the average than they are the median. Okay, this next example is out of section 6.1. It is about bone density, and I am measuring bone density in the forearm and also in the spine of postmenopausal women here. And here are all of my summary statistics, my p-value from my t-test, and then the lower and upper endpoint from my statistical analysis. Let's start with 7A here. All of the difference need to be exactly 0 before we conclude that a statistical way that forearm can be used as a substitute for spine. That's going to be false. That's way too much to ask that all of the differences be exactly 0. We want them to be near 0 and maybe have an average close to 0, but they don't need to all be exactly 0. If the differences are all 0.2, 0.2, 0.2, 0.2, 0.2 all the way down, then the average would definitely be 0.2, but the standard deviation would be 0 there, right? If they're all the same value, then the average distance back to the middle is going to be 0. So B is true, but C is false. The average difference of 0.275 suggests that people in the study have forearm bone density tends to be higher. Well, that has to do with how the differences were computed. So here, forearm minus spine, that is going to be higher. So that's, if that's positive, that means forearm's going to be higher. So that statement is true. What are we doing here? The p-value is 0.03. For this test here, there is a difference. This p-value allows us to conclude that it's reasonable on average to use this as a substitute for spine. That's actually false, because if the p-value is less than 0.05, which it is here, then we do have a difference between the forearm and spine, right? The research question is supported. So we do have a difference. That would mean that it is not reasonable to use this as a substitute, right? The lower and upper say on average that forearm t-scores will tend to be higher than spine. Let's go back up here. This interval is completely positive. Okay, all positive, so that doesn't go down to 0. 0 would be where they're the same. This is an entirely positive interval, so that means whatever I put first is going to be higher. So on average, I can say that the forearm is higher than the spine here. So that is going to be true. Okay, the next one is about section 6.2. This is about our vitamin example that we looked at in class, and I'm doing a comparison between the females and males here. The difference was computed as actual minus DRI, so just like we were doing in class. I don't think we looked at iron in class, but here it is on the practice test. Here's my CDF plot for this data and also my summary statistics over here as well. The intake for iron cannot go below 0. Thus, the average for females should be positive instead of negative. That is false, because what I'm looking at is how much they're undereating or overeating on the iron. So I can have a negative here. That is fine. Okay. We're not looking at the actual iron intake, but we're looking at actual minus DRI. And if that's negative, that means women are not getting enough iron. A comparison of these averages suggests that for students in this study, males are taking in more iron relative to their relative to their daily recommended intake. That is definitely true. The males are positive here, actually pretty large. Females are negative, so males are definitely taking in more relative to their daily recommended intake. A comparison of these averages for all WSU students, males, this is going to be false. Okay, I need a p-value. If I want to extend my scope of inference from these individuals here in this study to all, I need to do a p-value analysis. I cannot look at just these two and make conclusions about all WSU students. That's where my t-test would come in and help me. The CDF plot suggests a majority of females are taking in less. That is true here. Here's the female line for the iron difference. And you can see that about 75% are actually below 0 there. So clear majority of the women are not taking in enough iron. In contrast, all of the men here are taking in enough iron. Even the male that was the closest to target was positive. So all of the males were taking in enough iron in this particular study. The number of females is different than the number of males. The fair comparisons cannot be made. That's false. So you don't have to have the same number in each group. Okay, this was just one about identifying the different components. So smoking status is not numerical, that's categorical. That's my grouping variable. BMI is numerical. BMI is a naturally numeric scale, so that's that. A t-test is used to test the average. I'm definitely looking at the average here of two groups. So a t-test is done to look at the average across two groups. So that's going to be the answer there for C. And then my scope of inference. The scope of inference has to do with kind of the stem of the problem here. You can see that it's American high school students. I think that's good enough there. Either smokers or non-smokers. So the individuals who took part in the study, well, those are American high school students, so they would be included in your scope of inference. American high school students who smoke, yep. American high school students who don't smoke, yep. Anybody in the world? No, these are American high school students, so we probably shouldn't extend to any high school student in the whole world. And then American high school students in 1970? No, I would anticipate that the trends have changed between 1970 and 2005, so I wouldn't anticipate that it would be a good idea to include 1970 in our scope of inference. So we'll put no there for that. This last one's out of section 7, which we were talking about today in class, actually. I got vitamin A, vitamin C, calcium, and iron on the screen. So let's take these one at a time. Females tended to take in an appropriate amount of vitamin A. So looking at vitamin A, females are the dotted line. That is really close to that target there. So I'm going to say true on that one. Males tend to take in an appropriate amount of iron. Looking at iron, the solid line is males here. That is false. They tend to be taking too much. Okay, they're clearly above our target line here. C, females tended to be closer to the daily recommended intake for vitamin A than males. So where is vitamin A again? Here's what I have for females. Really close to target line. Males, close to target line when the BMI is low, but when the BMI is high, you can see that I start to deviate from target there. So that is true. C is true. If BMI has no impact on intake, then the line's going to be flat. So that is true as well. You can see these here, vitamin C are pretty flat, or the vitamin A female line is pretty flat. Again, that means that BMI does not really having an impact on whatever my Y is, which here is amount off of target. The effect of gender is about the same regardless of BMI in regards to the appropriate amount of calcium intake. So let's look at calcium. What we're looking at here is how much of a difference the effect of gender is just how different are the two lines. And that looks like it's about maybe 400 or so on the difference scale here. It's pretty close to the same whether you're not at low BMI or high BMI. It might be a little bit smaller here, but generally, if these two lines are parallel to one another, okay, then the gender effect is going to be the same, irregardless of BMI. Okay, so what we're looking for there and trying to answer that one is, are the lines close enough to parallel to one another? Last one down here. This is just a little variation to what we did in section 6.1. Here we're going to actually be testing greater than 45 seconds. So not testing a difference equal to 0, but just wanting to know if a set of measurements, what am I doing here? Perceived elapsed time, if that's greater than 45 seconds. So I'm going to set up my statistical hypothesis test, okay, under the situation of no difference, or under the situation that it is equal to 45. Okay, so A is going to be the correct outcome here for that. Now, we are trying to figure out whether or not the actual or the mean time is bigger than 45, but I would do that with my checking to see if I'm an outlier on the right side of the distribution if I'm talking about greater than 45. But the reference distribution is going to be set up with an average of 45 under the null hypothesis. Okay. This research question goes in the alternative hypothesis. The null hypothesis is going to be equal to 45. So A is there, is correct. And then when we're trying to determine the p-value, the reference distribution here has to be centered at 45. So version A is going to be used to get a p-value. My p-value, right, is trying to determine whether or not my data outcome, my data value or my data outcome here is about 47, almost 48. The p-value is going to be trying to determine whether or not 48 is an outlier or 47.85 is an outlier. Doesn't look like it's going to quite be an outlier there on the upper side. But version A is the correct distribution that we would use as the reference distribution to compute the p-value. Okay, that does it then. That's our video for the study guide for exam 3. Good luck and we'll see you Wednesday.